We're going to number our 24 vertices, 0 through 23. And I'm going to use this notation. Something like this is going to represent a segment joining, for example, the second and the fifth vertex. We're going to do casework on the lengths of the segments. When I write D is equal to 1, this is our first case where each segment joins adjacent vertices. There are 24 total segments that join adjacent vertices. We have a segment that joins vertex 0 and 1, 1 and 2, 2 and 3, and so on. And the last one will join vertices 23 and 0. A vertex will join exactly one segment. Without loss of generality, let's choose the segment that joins vertices 2 and 3. If we choose this segment, then we cannot also have the segment that joins 1 and 2 because it shares vertex 2. We also cannot have segment that joins vertices 3 and 4 because it shares vertex 3 with our chosen segment. All 24 segments are listed here, and we need 12 or half of them. Once I've excluded segment 3 and 4, then I want to choose the segment that joins vertices 4 and 5. If I had instead chosen the segment that joins vertices 5 and 6, I wouldn't be able to get 12 segments. So I'm also going to pick the next segment over here, 0 and 1. So I can select half of the segments from this list, or I can select the other half. This gives me two ways to select segments with a length that I'm calling 1. Let's try D equals 2. This represents segments that skip over one vertex. So for example, a segment that joins vertices 0 and 2. I'm going to make two lists of these segments because I want it to be clear what happens when I select a segment to go into my set. These segments in order share a vertex with the segment that comes before and the segment that comes after. Notice that all of these vertices are even. Our last one in this set is 22 connecting back to 0. The remaining segments will have vertices that are odd. If we start with 1, 3, it's going to share a vertex with 3, 5, and so on. Again, we have a total of 24 segments divided into two groups of 12. 12 of them with even vertices and 12 that are odd. We're going to pick 6 segments each to be in our subset of 12 segments that don't share a vertex. Again, without loss of generality, if we choose segment 4, 6, we must exclude 2, 4 because it shares vertex 4, and exclude this vertex because it shares 6. But we need to choose 6 of these segments, so I'm going to go ahead and choose 8, 10, and 0, 2, and every other segment from there. Alternatively, I can choose the other half of the segments from this set. So that's two ways to choose segments whose vertices are even. None of the segments in the second group share a vertex with the segments in the first group, so I can independently choose one of two halves of the 12 segments that have odd vertices. So the number of ways that I can choose 12 segments, 6 from each of these groups, with this same length is 2 squared or 4. Now let's try D equals 3. Here we're joining vertices where we skip 2 in between. And I'm going to put them into groups, listing them so that consecutive segments share a vertex, and the segment joining vertex 21 and vertex 0 is our last one. Notice that all of these vertices are multiples of 3, and I think it's easy to see that we're going to have a second group of segments with the same number that are going to have vertices that are one more than a multiple of 3 and 2 mod 3. So we'll have 8 in each group. That's our 24 total segments divided by 3. If we want 12 segments in our subset, we're going to need to pick 4 from each of our 3 groups. And again, we can alternate. We have two ways of picking segments whose vertices are multiples of 3. Same thing over here and here. So for D equals 3, we have 8 ways of choosing our 12 segments. Now we'll go on to D equals 4. Starting with vertex 0, we have 0, 4, and 4, 8, etc. All these vertices are multiples of 4, and we can choose alternating halves in 2 different ways. That's going to be true for vertices that are 1, 2, and 3 mod 4. And again, in each of these 4 categories of segments, no segment in one category is going to share a vertex with a segment in another category, so all of these are independent. This gives us 16 ways of choosing segments where D is equal to 4. Now we'll try D equals 5. If we start listing out consecutive segments that share a vertex with the previous as we've done, we're going to realize that eventually we're going to hit all of the vertices. Here are all 24 segments, all in one category. This is a consequence of the fact that 5 and 24 do not share any primes. We can still choose every other segment as before. There are an even number of segments, so we can choose one half or the other, and there are two ways of choosing subsets of segments where d is equal to 5. Now we'll go on to d equals 6. We have 6 mod 6 residuals with 24 segments. That gives us 4 segments in each category. We can choose one half of the segments in each category. That's 2 of them. Or we could choose the other half. 2 choices for the multiples of 6, 2 more for each of these 5 residuals independently. That's 2 to the 6th, or 64 subsets. Let's go on to d equals 7. Again, we have that the GCD of 7 and 24 is 1. So if we list these in consecutive order, each time sharing a vertex with the previous segment, we're going to get all 24 segments in this category. We can choose one half of them or the other, so that's 2 ways. Let's see what happens when d is equal to 8. We'll start with the vertices that are a multiple of 8. So this segment joins 0 and 8, 8 and 16, and then 16 back to 0 again. And we're going to get the same thing for vertices that are one more than a multiple of 8. We have 24 total segments, and we're going to divide them up into our 8 mod 8 residuals. So as we see, we're always going to have 3 segments in each. The trouble is, if we want to produce a subset with 12 segments, we need some of our subsets to produce 2 segments. But no matter which segment we choose from the 3 in each category, we'll have to exclude the other 2 segments. So it'll be impossible to draw 12 segments with this length. So there are no solutions for d equals 8. We'll go on to d equals 9. We'll start by joining consecutive vertices that are multiples of 9. This takes us to 3. So it turns out these vertices are all multiples of 3. In the next category, we're going to be drawing segments that join vertices that are one more than a multiple of 3. And then 2, 5, and 8 in mod 9. Each of these categories contains 8 segments, and we can choose half of them or the other half independently for each category. 4 segments in each category, and there are 8 ways to do this. For d equals 10, let's start with the segment that joins 0 and 10. By the time we've made our way around the circle, we've generated 12 segments where all the vertices are even. So we'll be able to create another set of segments where all the vertices are odd, and that will also contain 12 segments. So we'll pick 6 of these from each of them, and there are 2 ways of doing that for 4 total ways where d is equal to 10. When d is equal to 11, we again note that the GCD of 11 and 24 is 1, so we're going to cycle through all the vertices, generating 24 segments. There are 2 ways to choose 12 segments that alternate in this list. Our last one is d equals 12. One segment that we can pick is 0, 12. It's not going to share a vertex with any other segment. We can also create segment 113 to 14 and so on. There are no other segments with this length that share vertices 1 and 13 or vertices 2 or 14. Here we have 12 segments of the same length and 1 way to choose them. So now we can total up over all the different segment lengths. Here we have 2, 4, and 8, 16, 2, and 64, 2, 0, and 8, 4, 2, and 1. This adds up to 113. If you'd like me to solve any other math contest problems, please leave them in the comments.